This is Calculus AB 2016 AP exam question number 1. This is Calculus AB 2016 AP question number 4. Okay, they say consider the differential equation. So this is a slope equation. Okay, and it says dy dx, so that's a derivative, that's a slope equation. And it says on the axis provided, sketch the slope field for the given differential equation at the 6 points indicated, just at those 6 points that they have there. Okay, so let's go do that part. Now, I'm doing very formally. I wouldn't go through all this, but I would be very careful because this is just simple arithmetic and I don't want to make a mistake. You always need to get points where you should get the points. Don't rush through something that's easy, make a mistake, and lose a point. So this is, I think it's probably worth about 2 points to do this, okay? So what we need to do, these points are, I listed the points here. Say I want the slope at the point 0, 0. This is point 0, 1, 0, 2. This is 2, 0, 2, 1, 2, 2, okay? So just so I'm not making mistakes here. And then you just plug in 0 for x. Be careful, make sure you plug the right one in for the right one, and 0 for y. Now you can sort of do these in groups. For these three, when x is 0, so the denominator becomes -1. And then when x is 0, when y is 0, y squared is 0. When y is 1, y squared is 1. When y is 2, y squared is 4. So the slope here is 0, the slope here is -1, the slope is -4. That means at these points, the curve, the slope is 0, -1, and -4. Okay. Now, when you're doing these, be very careful. Zero slope is very important. You need to really show that. For negative slopes, you got to make sure they're going down. You don't have to worry too much about how steep they are, but I would try and make the -1 at about a 45-degree angle. Okay, and then you should make sure that -4 is steeper than -1, so just show it's being a little steeper. Okay, at these points here, when x is 2 for all three of these. So when x is 2, 2 minus 1 is 1, so the denominator is 1 for these three. And then you're plugging in the same values for y as you did in the first three here. So when y is 0, y squared is 0. When y is 1, y squared is 1. When y is 2, y squared is 4. You get a slope 0, 1, and 4. Slope 0, positive slope now. 1 is a slope about 45. Positive slope 4, just a little steeper. Okay? Don't make too big a deal of that as long as you have positives, negatives, and zeros correct. Okay? This next part of the question says, let y be the function of x, be a particular solution to the given differential equation with an initial condition. Okay? When it gives us an initial condition, we can find the particular solution. If we were to integrate, we would get a general solution. We'd get plus c. We want the particular solution that goes to the point 2, 3. Okay, so, and then it says, write the equation of the tangent line to the graph of this function at x equals 2. And it says, use your equation to approximate f of 2.1. Now, we're not finding the particular solution in this part. We're just writing the equation of the tangent line to that function at x equals 2. So in order to write the equation of the tangent line, like writing the equation of any line, we need a slope and a point. And it looks like I spelled slope wrong. Okay, and the point is, you be careful about this because a lot of people make this mistake. F of 2, f of x, f of 2 is equal to f of x equal to y, which is 3. Get those correct, okay? And so we have the point, now we need the slope. So the slope, y squared, so y is 3, so that's 9, and x is 2, 2 minus 1 is 1. So the slope at that point is 9. Now remember, the best way to write the equation of a line is by point-slope form. Now, most of you are locked into slope-intercept form. I would suggest you learn point-slope form. It's not too complicated. If you know the slope equation, slope is change in y over change in x, then you basically know the point-slope form equation of a line. You just simply multiply by delta x. Okay, you see what I did here? So it's m times delta x, and delta x is just a change in x, so it's x minus x point, and delta y is a change in y, which is y minus y point. Now you just have to plug the stuff in. So the slope is 9, so you plug 9 in for m. X point is 2, y point is 3, so here it is right here, and then I just move the 3 to the other side. So y equals 9 times x minus 2 plus 3. You do not want to do any more with this because you're going to make the problem harder for yourself. Okay, so here's the equation. I just rewrote up here. Now it says approximate. Use this line to approximate f of 2.1. In other words, if I knew the function, I would plug 2.1 in. They want us to use this line to approximate it. This is called local linear approximation. Okay, and I'll show you a little bit about this later. So when the point is x is 2.1, in this format, it's very simple because if I plug 2.1 in for x, you see right here 2.1 minus 2 is 0.1. 9 times 0.1 is 0.9 plus 3, 3.9. So it's much easier calculation. Okay. The third part of this says, this is where you're going to get the most points, by the way. This says find the particular solution to the given differential equation with the initial condition f of 2 equals 3. Okay. The most important step here is you start with the differential equation. Okay. The most important step is we call it separating variables. That means I have x's and y's. I want all the x's on one side and all the y's on one side. And by the way, we always want the dx and the dy in the numerator. So the simplest way to do it is do not move the dy. Okay, we need to move the dx up. And the only y I see over here is y squared, so I'm just going to divide by y squared. So right here now we have the differential equation, but we've separated variables. See, all the y's are over here, all the x's are over here. That allows us to integrate now, okay? So this side we're going to integrate with respect to y, this side we're going to integrate with respect to x, okay? Now in order to do the integrals, y squared, it becomes y to the minus 2 power, so I can use the power rule here. So this becomes y to the minus 1 over y minus 1. And when I differentiate dx basically over x, is the natural log of the absolute value of x. In this case, x minus 1, if I did a u substitution, du would be also dx. So it's not going to be any different, okay? So the derivative of dx over x minus 1 is the natural log of, be careful, absolute value of x minus 1. And then you always have a constant of integration. Now, I could put a constant of integration on this side too. It is acceptable when you're doing differential equations like this. If I was to put a constant on both sides and then move the constants together and added them, I just simply get another constant. I'm not going to go through all that. And it is acceptable then just to put the constant on one side. And it's probably good practice to put it on the side where the x was when you integrated with respect to x, because usually we're going to just simply solve for y. Okay? So I did one more step here. I put minus 1 out front, or positive divided by negative is a negative, and y to the minus 1 power becomes 1 over y. Okay? And I'm not going to do any more with this. Now I'm going to find the constant of integration. So they said find c. We're going to find c using the initial condition, the 0.23. So this is not a difficult step. X is 2, so we're going to take this equation right here, and I'm going to plug 2 in for x, and I'm going to plug 3 in for y. And now I just have to solve for c. And it's usually pretty straightforward. You need to know this is 2 minus 1 is 1. The natural log of 1 is 0. You need to know little things like that about logs. Okay? And so this is 0. So c becomes minus 1/3. So now I took this equation where I was looking for c. I did my substitution, found c. That's where I go back and plug c in. C was minus 1/3. And I'm going to write it right here. Now for this question, these questions are usually worth about 4, 5, 6 points. And by getting to this point right here, you've gotten almost all the points, okay? There's usually one more point for solving for y. And some of you may struggle with that a little bit. So if you're really stretched or if you're having problems, don't get too uptight. You've gotten most of the points already, okay? So to solve for y, the only thing I'm going to do is I have 1 over y here, so I'm going to take the reciprocal of this side, which is y. I take the reciprocal of this side. It must be the reciprocal of the whole thing, so it's 1 over the entire expression. Okay, so here's my equation, but I didn't get the whole point yet, because you got to understand that an absolute value is a piecewise function. So this curve is in 2 pieces, or at least 2 pieces. Okay, and the way you break it up, and we need to know which branch we're going to use of this function. Okay, so if you understand, if I have an absolute value, I need to know when what is inside is either positive or negative. And so obviously I'm always going to look to see where it's equal to 0. So when x is 1, this is 0. So this is where this function breaks up, at x equals 1. So I need to know, I need to consider when x is greater than 1 and when x is less than 1. So I'm going to do it for you here just to show you. So the absolute value, I'm just looking at the absolute value of x minus 1. When x is less than 1, because that's what breaks up, when x is 1, this is equal to 0. When x is less than 1, say 0, minus 1, minus 2, this expression inside is negative, which means to drop the absolute value, I need to take the opposite of what's inside. Okay? When x is greater than 1, this is the other branch. If x is like 2, 3, 4, 2.1, it doesn't matter. When x is anything greater than 1 in here, that would make this a positive. And so in order to get rid of the absolute value, I don't need to do anything to it. It's just x minus 1. So there's my two branches. So when x was, when x is greater than 1, I don't need the absolute value. So I just rewrote this expression right here, drop the absolute value, and I put x minus 1. If x is less than 1, I need this expression right here. So I drop the absolute value and plug that in for it here. Now the question is, which branch are we talking about? Okay, well, that's pretty easy. If it has to contain this point, okay, that means if I plug 2 in for x, I should be looking over here, if I plug 2 in for x, this is positive. Or you could simply look at it, x is greater than 1. When x is greater than 1, I want this branch. So this is the branch I'm looking for. If you notice, if I plug x is equal to 2 in here, I get 2 minus 1 is 1 minus, so I have the natural log of minus 1, which is not defined, okay? So this is the branch we're looking for. The way you determine it is by which branch contains this point, okay? So there's my answer to that. So let me give you a little bit of visual I was talking about part B. Here's the graph of this function. This is the graph. By the way, I broke it up into the two branches. Now, you don't need all of this. I'm just trying to give you an idea what's going on here. Here's the one branch, the red branch, is the branch where inside was negative, so we had to take the negative of the absolute value. And the other branch where inside the absolute value is positive, we just drop the absolute value. So there's the black branch. And where our point, you notice the point 2,3 is over here on the black branch. Okay? Now, if you remember, they had us write the equation of the tangent line at the point 2,3. So this blue line, this blue dashed line is the tangent line to the curve, to this branch of the curve at the point 2,3. Now this is why this is called local linear approximation. If I wanted to find f of 2.1, if I was to plug 2.1 in here for x, that means I'd plug 2.1 in here. That means I'd be taking the natural log of 1.1, and without a calculator, I don't know what that is. But if I did, I would have to subtract it from 1/3, which is going to be some ugly decimal, and then divide it into 1, which is kind of a complicated operation, okay? Or just complicated arithmetic, I should say, okay? Okay, this is called local linear approximation. If you'll notice, I'm looking for the value on the curve at 2.1. So 2 is close to 2.1. That's called local. Linear is a line, okay? So if I draw the tangent line to a point where I'm looking, close to a point where I'm looking on a curve, okay? I drew the tangent line. If you notice, when x is 2.1, I drew this vertical purple line here. If you notice, the curve and the tangent line are both in the same, they're very close, okay? So whether I plug 2.1 into the function, and I got some ugly arithmetic, which I had trouble with, or I plug 2.1 into the tangent line. So you see what happens when I plug the 2.1 into the tangent line. It's a very easy operation. 2.1 minus 2 is 0.1. 9 times 0.1 is 0.9. Add 3, 3.9. So here's the approximation, was 3.9. And I actually did the calculation. If you plug it in here, I used my calculator and plugged 2.1 into the function, and I got 4.2. So you notice here, they're fairly close. Normally, this would not be a very close approximation, but they're just giving you the idea of what you're doing there. Okay, so this is called local, close by, linear, draw a line, it's an approximation to the value. Now I want to show you a reason here of why you don't want to use slope-intercept form. What I did is I changed this to slope-intercept form. Okay, this is the same equation, only in slope-intercept form. If I did that, it's more work actually to write it in slope-intercept form. And if I plug 2.1 in for x now, in here, I have to multiply 9 times 2.1, which is not that difficult, but it's a little more arithmetic. And then I got to subtract 15. It's a little more complicated, more chance of mistake. Okay, so point slope form is easier form to get it into, and it's much easier to make the approximation. All right, let's look at the points they gave us. In our first part here where we had to draw different slope fields, we had 1 point for 0 slopes. You usually always get a point, 1 point for the 0 slopes and 1 point for the non-zero slopes. So you had to make sure these were negative, and I would make sure if they're a high value, they're steeper. And these are the positive slopes, and if it's a higher value, it's steeper. Okay, so there's 2 points there. And again, this is really pretty easy to do. You don't want to lose those 2 points. Equation, you get 1 point for the next one was where you use the local linear approximation or writing the tangent line. You got 1 point for the tangent line for the whole thing. So you had to find the slope and then use the point and just simply plug it into point slope form, and then 1 point for the approximation. Okay, so there's 2 more points there. That's a pretty quick points. For this last part, we had to find the particular solution. Okay, you get a point for separation of variables. Now, something that's really important to understand. If you notice down here, note 0 out of 5. This is worth 5 points. You got 0 out of 5 points if you did not separate your variables. So you'd lose everything if you didn't separate your variables. Okay, you got 2 points for the antiderivative, so that's probably 1 for each side. And then you got 1 point for the constant of integration and using the initial condition. Okay, so this is where most of the points come from. And then there's the last point for solving for y, which I had mentioned. Okay, so you can see you could have just stopped right. Well, if you went here, you'd find c and plugged it in. You'd at least gotten 4 of the 5 points. Okay, and remember the integral of dx over x minus 1 is the natural log of the absolute value. Let me show you one more thing. Again, this is not necessary to solve this problem, but just to show you, if I've drawn different curves here. Each of these curves, we're all using the same slope field, but each of these fields has a different point that you plug in to find the different c's. So here's the red curve that we did in our problem. C was 1. I didn't break these up, by the way. C was 1/3. Okay, and here's a curve where C was 1. Here's a curve where C is 2. They're all the same exact equations. I'm just changing the constant of integration. Okay, so this is what we call a family of curves. That's why an integral is an indefinite integral. You get a family of curves. You get the plus C. Okay, and what I would just show you here too is I'm going to show you a whole bunch of slope fields. So I'm just going to quickly go through here, and I'm plotting just like we did at the beginning, slope fields that you would have done if they asked you for specific points. So you can see I'm just doing this rather quickly here. So let's see what's going on here. So if you notice though, each of these curves, this is what a slope is. I just took this equation and I plugged all these different points in here and found out what their slopes were and drew the little slope fields. Now if you notice, every one of these curves, when it goes through here, you can actually see what a function would look like. You can see it sort of comes down this way and it goes in here and then it goes up over here. So you can see every one of them, and even though they don't go right through these points here, if I did more of a slope field at more points, you could actually see it better. But if you notice, the curve is always tangent. If you put a point here and do a tangent line, it's always tangent to the slope field. You see how it's tangent. So if you want to draw a curve in a slope field, you just follow the slope lines. Okay, and it just gives you an idea of what the constant of integration does. Again, this is not necessarily for this question, but it might help you understand these problems a little better.